In this video, we are going to look at alien dictionary. Let's look at the question first. There's a new alien language which uses the Latin alphabet. However, the order among letters are unknown to you. You receive a list of non-empty words from the dictionary, where words are sorted lexicographically by the rules of this new language. Derive the order of letters in this language. And here are some examples we can look at first to help us understand the question better. Look at the first example. I want to look at the words pair by pair. Let's first look at the first two words, and we know letter T must go before letter F, because WRT is before WRF. And look at the second pair, WRF and ER. We know W is before E. Is before E. And let's look at the third pair. We know R is before T. And look at the last pair. We know E is before R. This is the order we get from this. This is all the information we get from this array of words. And so we can summarize the information we get and come up with this output here. So we know T is before F, and R is before T, and E is before R, and W is before E. So T, F, and looking at this, E is before, look at this, R is before T, so R is here. And look at this, E is before R, so E is here. And W is before E, so W is here. So this becomes our output, which is the same as this. And let's look at another example. This one is very simple, because we only have two letters in our dictionary. It's X and Z and X. Z comes before X, so the output is just ZX. And another example here. So from this example, we know Z is before X and X is before Z, which is impossible. So the output is just empty string. And for the last one is a very interesting one, because we can't really get any information from this array of words. We have ZA and ZAV, and the first part of the second word is the same as the first word. So we don't really get any other information. And we can just output any order of the three letters, and it's a valid solution. Understand the question now, and we can go into more detail about the solution. Let's still look at the first example. So based on the explanation of each example, we know we want to compare words pair by pair. So the first pair is WRT, WRF. And from this pair, we know T is before F. And we want to construct a graph using the information we get from the array. In this pair, we know there's an edge between node T and node F. And T and node T has an arrow pointing to F, because T is before F. And for the second pair, we have WRF and ER. In this pair, we know W is before E, so we can construct this graph using the pair. And the next pair is ERETT. From this pair, we know R is before T, and we don't have a node R, so we want to construct a node first, and then want node R to pointing to node T, and we already have a node T here. We just want R to point at T. And the last pair is ETT and RFTT. From this pair, we know E is before R. And we already have a node E here, and we already have a node R here. We just want E to point at R. And this is our final graph. This is our final graph. And we just want to run topological sort on this graph, and we can get the answer. And let's do it. So we want to use a stack. You can also use a queue or just a set. It doesn't really matter what data structure you use. So we first want to put the starting point into our stack, and based on this graph, the starting point is W, because W doesn't have any incoming arrows. This is our starting point, and we put it in our stack, and this is our output. Let's first pop W out of our stack and put it into our output. And let's look at all the outgoing arrows from node W. There's only one, it's this one, and it's pointing to E. Let's remove this arrow, so E doesn't have any incoming arrow, and E becomes the new starting point. We put E here. This is our new starting point, and we pop out E and put it into our output. And let's look at this arrow, and we remove this arrow. After we remove it, the node R here doesn't have any incoming arrows, and R becomes the new starting point. And we pop R out of the stack and insert it into our output. And let's look at this arrow here, and let's remove it, and T becomes the new starting point. It's already removed. We put T into our stack, and in the next iteration we pop T out of the stack. And look at this arrow, we remove this arrow, and then F is the new starting point. We put F into our stack and remove it, and I forgot to put T into our output, and we pop F out from the stack and append F into our onto our output. And this is our answer for the first example. And let's summarize the steps we have done. So first, we want to construct a graph using the words in the dictionary. And in more detail, we compare adjacent words and construct nodes. So the second step is just run topological sort on the graph. And so as we run the topological sort, we also want to generate the output. So we generate the output. So this is the steps. And let's look at the data structures we used. So we used a node. So first we want to construct a node class, and node must contain something. It must contain the neighbors. So if we know the neighbors of the current node, we have the arrows. And we want to use a stack to keep track of the order of the output. So this is two things we have used so far. And let's look at the last example. So it's this one here. This example is an edge case for this question, and it gives us more information about what kind of data structure we need to use. So this one is ZA and ZAB. So by comparing these two words, we don't really get any information from it. We don't know the ordering of any letters. In this case, we want to store all the letters in somewhere. We can't even construct the graph. We just randomly get things from the place that stores all the letters. and that's going to be the answer. In this case, we can use a hash set or just a set, and every time you see a word, you put all the letters in the word into the set. So the set contains all the letters have seen. And once you construct a node using a certain letter, you want to remove the letter from the set. So if node exists, remove from set. So in this case, we don't need to worry about if our graph is empty, if we are able to construct a graph or not. We always have all the letters there. So if the letters doesn't exist in the graph, we can just get it from the set. Yeah. So another data structure we need to use here is a set. And this is the things we need to use to implement this question.